My name is Dongpeng Xu, coming from the Penn State University. Today I'm very glad to be here to present our recent work about crypto function detection tool in obfuscated binaries. This technique can be used for malware analysis and malware detection. So the technique is called bit-precise symbolic loop mapping. This is a joint work of Penn State and UT Arlington. So I will first start from a brief introduction of the background knowledge about crypto functions. So in this talk, the crypto function means the encryption and decryption procedure. So as we all know, there are lots of different applications of crypto functions. So first, from the bright side, crypto functions can be used for sending and receiving messages via untrusted channels. And also they can be used for signing and verifying some digital signatures. And on the other hand, in dark side, malware authors can use crypto functions to hide malware signatures and also use them to create malware packers and work around firewalls via some encrypted channels which are invented by the malware developers. And at last, crypto functions can also be used by malware developers to create ransomware. So if you do a search online for the crypto functions in malware, there are lots of this kind of news reminding people that this is a more and more important problem nowadays. Especially recently, the very famous ransomware called WannaCry, it can encrypt users' file and data and encrypt them and ask the users to pay a ransom. Otherwise, their data and file will be lost. So given that there are lots of these kind of crypto functions in malware, so it provides challenges for malware analysis and malware detection. So if we can identify those crypto functions, it will be very helpful for malware analysis. So generally speaking, there are several advantages. First, crypto function detection can provide a starting point for reverse engineering for packed malwares, because the true malware behavior will happen after the decryption procedure. And the second one is that usually security analysts want to pay attention to the true malware behavior, usually not the unrelated encryption and decryption functions. So if we can identify those functions, it will provide and it will save time for those malware analysis. And third one is that since ransomware usually use encryption and decryption procedure, so if we can identify crypto functions, it will provide some help for identifying ransomwares. And at last, some malware developers can customize crypto functions. So if we can identify those customized crypto functions in other programs, then it is very likely that those programs are malwares from the same author. So, so far we have answered the question that why we need to detect crypto functions. So the next question is that how? Fortunately, there are some attributes in crypto functions that we can utilize to detect them. First is that crypto functions usually have lots of bitwise operations like AND, OR, negate. The second one is that usually crypto functions are it have very core transformations, which can represent the semantic of the crypto algorithm. Usually, they are implemented as several loop structures. The third one is that crypto functions are usually standard-based. There is a kind of very detailed algorithm specification about a given crypto function. And at last, crypto functions usually they have lots of well-known reference implementations, such as some open source libraries. So the existing method have used this, utilize these kind of attributes to to check crypto functions. Generally, there are two categories of methods, static methods and dynamic methods. So in static methods, lots of these static methods are heuristic-based. They detect crypto functions by by using some heuristics like entropy and some magic constant values and so on. Another group of static method is program analysis-based. They use some signatures like data flow graphs to identify the crypto functions. And on the other hand, in dynamic method, most of these kind of methods rely on identify the input and output relations. So here I show an example here. Suppose that f is a function. We want to check whether f is an implementation of TEA, which means tiny encryption algorithm. So first, we can fit the same input in both f and TEA. Then we check the output. If the output are the same, then it is very likely that f is an implementation of TEA. So it's like a testing style method. But unfortunately, there are still some challenges to those existing methods. So first, in static methods, for the heuristic-based static methods, because those heuristics they rely on is usually they cannot catch the essential semantic of that crypto algorithm. So they may suffer from false positives and false negatives. For those static methods based on signatures, those signatures can be hidden by obfuscation techniques. On the other hand, in dynamic methods, actually they can resist some kind of control obfuscations. But the problem is that they rely on identify the input and output relations, but there are existing some existing methods like data obfuscations and customized crypto algorithms, which can change the input and output relations. So here I show an example of a simple data obfuscation. So in the normal version of the program, there are two 16-bit integers, variable A and B. But in the obfuscated version, there's only one integer, 32-bit integer variable x. Actually, it is a combination of the A and B in the normal version. But if you use dynamic method to detect this kind of programs, they cannot identify the input-output relations since the number of input variables are different. They usually treat these two versions of programs are different. So this data obfuscation also inspires us that we really need a more fine-grained method to identify crypto functions. So here we propose our method to overcome the limitations. First is that it is a new solution to detect a crypto function. The technique is called bit-precise symbolic loop mapping. And our method can catch the fine-grained semantics of crypto transformations, and also it is resilient to control obfuscation and data obfuscation at bit level. So in one sentence, our technique do equivalence checking on loop bodies in the reference program and the target program. So here I'll show a big picture of the whole technique. First, we have two reference programs. We have two programs. One is the reference and one is target program. We run both of the two programs to get two execution traces. Here, the blue line means the reference trace, and the target line, the red line means the target trace. And then we run loop detection on both of the two traces to extract the loop bodies. After that, we run bit symbolic execution to transform the loop bodies into Boolean formulas, here fx and gx. So at last, we check whether those two formulas are equivalent. If they are equivalent, then we say a crypto function is detected. So generally, there are 6 steps in our technique. First, we need a reference implementation, and then we log 2 execution traces, and then we do loop detection, bit symbolic execution, and variable mapping, and at last we check the equivalence of the 2 formulas. So I will go through this whole procedure step by step. So first, the reference implementation. We need a reference implementation, which is usually selected from a very well-known implementation of the crypto function. So here, I show an example of TEA. The reference implementation should contain the core transformation of the crypto function, which can represent the semantic of that crypto algorithm. So here is the main loop body of the TEA. After that, we run both the reference program and the target program to get 2 execution traces. The trace contains runtime information like opcode, operand, register values, and the memory access value and addresses. After we get the 2 traces, we run loop detection on both of the traces. Actually, here we detect 2 types of loops. First is unrolled loop. It is actually like a series of repeated instructions. So here, in this example, there are 2 loop bodies. Both are instruction 1, 2, 3, and 4. Notice that here the address are different because they are unrolled loops. The second type is the loop body, which ends with jump instructions. So here in this example, there are 2 loop bodies, instruction 1, 2, 3, 4, and instruction 1, 5, 6. Notice that here a loop body could include a branch instruction. So different loop bodies, although they jump back to the same address, but the loop body could go to different branches in different executions. So the loop body itself could be different. After we extract the loop bodies, we run a bit symbolic execution on the loop bodies to transform them into boolean formulas. So here is our core contribution. We actually extract the fine-grained semantics of a crypto function. So in all those formulas, the variables here are all boolean formulas, boolean variables. So here I show an example of the reference formula and target formula. So x1, x2, x3 here are inputs of the reference formula, and the u1 and u2 are output variables. And similarly in target program, the y1, y2, and y3 are inputs, and the v1 and v2 are outputs. So the next step, we need to compare to check whether those 2 groups of formulas are essentially equivalent. So, but before that, we need, because there are actually 2 different formulas, we need to map the variables together so that we know how to compare them. For example, here we need to know which input variables in the reference formula is exactly the input in the target formula. So one simple way is just to do a permutation to try different possibilities. But since here in our formula, all the variables are boolean variables, so there's like usually hundreds of those variables. So simple permutation will cause performance problem. So here we propose a variable mapping algorithm to map the input variables and output variables. Due to the time limitation, I cannot go into the details of this algorithm. If you are interested, you can find more details in our paper. So here I only show the final result of this mapping algorithm. So we can map the input and the output variables. So given the variable mapping result, we can go further to generate the final equivalence checking equation. So first we replace the mapped input with a same symbol. such as here, we mapped x1 and y2, x2 and y3, and x3 with y1. Then we replace x1, y2 with A, x2, y3 with B, and x3, y1 with C. And after that, we also connect the mapped output variables together to generate the final equation. So this is the final equation we need to check. At the last step, we use a theorem prover to check whether those equations are actually equivalent. If they are equivalent, which means the target program, the loop body in the target program is essentially the same, has the same semantic of the reference program. So if they are equivalent, we say a crypto function is detected. So far, I have gone through all the steps in our technique. We evaluate this technique from 3 aspects. First one is from the effectiveness. We try to detect 5 crypto algorithms: TEA, AES, RC4, MD5, and RSA. We try use our technique to detect some the crypto algorithms in some common used crypto libraries like OpenSSL and libgcrypt with obfuscation techniques. And we also use our technique to check a customized crypto algorithm, which is an XTA variant. And also we use our technique to detect some malware samples. In our experiment, all crypto functions are detected. The second evaluation is about false positives. We feed some normal programs with heavy bitwise operations into our tool, and there's no false positives identified. And the last evaluation is the performance. Actually, one analysis usually takes like 15 to 40 minutes. And based on our observation, the loop detection is the most time-consuming part. So in summary, we propose a new method called bit symbolic loop mapping to detect crypto functions. This method can catch the fine-grained semantic of a crypto function, and it is resilient to control and data obfuscation. And we also have our tool, a demo tool, open sourced. You can download it and play with it and have fun. So thank you. That's all.
Questions? Yes, go ahead.
Yes, John Criswell, University of Rochester. So, interesting work. One question I have, though, is if your technique were to be deployed in the wild, then wouldn't attackers start using, say, modifications of existing algorithms? So, for example, maybe doing AES, but not doing as many iterations, or creating sort of ad hoc encryption algorithms that perhaps don't have cryptographic strength, but are just different from your reference implementations.
So you mean the malware developers can customize some crypto algorithms, right?
Right, because essentially what you're doing is a one-for-one functional match between your reference algorithm and the one that you're looking for, right?
Yeah. That's a very good question. Yeah. So actually, in our method, we can detect a kind of customized crypto algorithms. For example, in TEA, the malware developer can change the magic number in their personal implementation. But in our technique, it can be handled. But if they are using a totally different implementation, I guess our solution is that you can find a new reference implementation and put it into our library. Yeah.
Okay, let's chat afterwards. Thanks.
Thank you.
You explained some of the challenges of previous approaches. What's the drawback of the data flow analysis approach?
Oh, it cannot handle obfuscations because data flow, if you are using data flow graph as a signature, a simple obfuscation can totally mess it.
Right, but all you need to do is see when you change one input of data, does all of the output change? right? Like you rely on confusion and diffusion and say, does this look like a crypto algorithm? You're not pinning down the actual algorithm.
I'm sorry?
Right, you just say, does this obey cryptographic properties? If I change input slightly, all of the output changes.
Yes.
And that's completely resilient to obfuscation. It's just input-output dependent.
Yeah, that's dynamic method. I hear you are talking about data flow graph, right?
Well, you can do that just from the control flow, the data flow. Okay, let's talk.
Yeah, we can talk about these details.
My comment is very similar to the last one. If a loop is taking in data that appears to have some simple correlation, i.e. it's not random, and if the output is uniformly distributed zeros and ones, then it's a crypto algorithm, and it doesn't actually matter what the internals are. And I believe it's possible. I believe that someone will come next year with a paper that shows how they can obfuscate crypto algorithms so they don't even seem to be using arithmetic or Boolean operations. So I really think the definitive thing is, as the previous questioner said, what are the properties of the algorithm? If it's crypto, it's pretty easily recognized.
Actually, that's a very good question. I think usually crypto functions are not that easy to customize and to change. So it requires a very strong background knowledge. So essentially, the core part of that crypto functions is usually fixed. There are very small number of locations in that crypto function that the malware developers can change. So usually, our method can catch the core part of that algorithm. So usually, this core part will not be changed. Yeah.
So one last short question.
Just to add to the previous question, like you could have an obfuscation where a single loop is split into multiple loops, or multiple loops can be combined into a single loop. Since your technique checks the equivalence of loops from the reference implementation and the given implementation, how do you handle that kind of obfuscation where you combine multiple loops and you split the existing loops into multiple loops?
You mean how to combine the loops?
No. Let's say you have an obfuscation where you split an existing loop from the reference implementation into multiple loops.
One possible solution is that in the reference implementation, we can, because we are using one loop body, we can actually combine the two loop bodies in the reference implementation, so as like to try the different combinations. This is one possible solution. Yeah. Thank you.
Okay, so let's thank the speaker again, and this concludes our session. Thanks.